Now let's see what is meant by binary search tree. Okay. So it is a node-based binary tree data structure which has the following properties. And what are those properties? All nodes in the left subtree are less than the root node. Okay. So previously what we have done for considering a binary tree, so we did not consider any node values. We have just went with the help of indexes. We have traversed with the help of pre-order, in-order, post-order traversals. Right. Now, in this concept, you will consider the node values also. Okay. Every node value is important. Right. So, and all the nodes, all the nodes in the left subtree are less than the root node, and all the nodes to right subtree of the root node are greater than the root node. Okay, and there should not be any duplicate nodes. Duplicate node means any two nodes cannot be the same. Okay, suppose, and how this is actually represented is the elements in the left subtree are having less value than the root node, and root node will be less than the right subtree elements. Okay, this is how it is represented. Root node is root node is greater than left subtree and root node is less than right subtree. Okay, now let's see how to construct a binary search tree. Okay, now we'll see the operations that can be performed on the binary search. So now we'll see how to construct a binary tree, and also we'll see the operations, that is insertion, traversal, searching and deletion, that can be performed on a binary search tree. Okay. So now let's consider, I want to do insertion. My first node is 10. Okay. Always the first node will be my root node. Okay. Now I want to insert 16. What is my rule? Left subtree elements are less than root and root is less than right subtree. Okay. Now root is there. This is, next node is 16. So 16 will be placed to left or right. All the elements greater than the root node will be inserted at right. Okay. So this is added at right subtree. Okay. Now I want to add 6. Okay. Is 6 less than 10? Yes, if it is less than, you have to insert it left subtree. Now my next node is 17. First you went to 10. You have to start going, inserting elements from root node. Okay, now first you have to traverse root node, then you have to go to the next element. How is my search element is, my element to be inserted is 70. Now, is 70 greater? So we'll see. Is root node less than my new node? If the root node is less than root node, if the root node is less than right node, I want to insert it right. Or if it is less than, it is inserted over here. Okay. So obviously 70 is greater than 10, so it goes here. Okay. Now again, is 16 less than 70? Yes. Is 70 greater than? Is 70 greater than 16? Yes. So where it will go? It will go to the right side. Okay. Now I want to insert 21. Okay. So it went to 10. Is 21 greater than 10? Yes, it will go to the right subtree, but right subtree is filled here. You cannot insert over here another element. So from here you will check, is 21 greater than 16? Yes, it is also 16 greater. But here also another element is there. Okay. Okay, now you will check. Is 21 greater than 17? No, it won't come here. It will go to here. Okay, if it is greater only, it will go to the right subtree. If it is less than the particular node, it will go to the left subtree. Okay, now I want to insert 7. I went here. So in the you'll see, is 7 greater than 10? No. Then it comes to left subtree. But this is already filled. What should I do? I have to check it here also. Is 7 less than 6? Yes, it's greater than. The new node is greater than 6. So should I add it over here or here? So it is greater. So I have to add it at the right position. Okay, now I want to add one more element. 4. Okay, so I went here. Is 4 less than 10? Yes, it goes to left subject. Is 4 greater than 6? No, it won't go here. Is 4 less than 6? Yes, it will go to the left subject. Okay, so this is how you insert elements in a binary search tree. Okay, so next one is insert. Next one to insertion is traversal. You have already done traversal. How you want? If you want to insert elements, you have to traverse from the root node to the next nodes. And if it is less than that root node, you will go to the left subtree and you will traverse every element. Okay. In case if the element is greater than, in case if you want to insert a greater element than the root node, you have to traverse the right subtree. Okay, you have already traversed the right subtree. In case if this after completion of this entire tree, if you want to find the pre-order, in order also, you can do it with the help of, we have seen the formula for LNR, LR, and like this, right? You can also find it like that. Okay. So insertion is done, traversal is done. Now searching. What is meant by searching? Finding, trying to find an element from a particular, tree. Okay. Then it's just like the binary tree. So for suppose you want to search an element 4. First you went to the root node. Is root node greater than or less than the search element? The root node is greater. So in which way you have to, find the element. Okay, this is my root node. Okay, the elements right side to root node are greater than the root node, and the elements left side to root node are greater than the and the elements left side to root node are less than the root node. Okay, now what should I do? I have to find the location of 4. So 4 is less than 10. So should I go to left or right? Yes, I have to go to the left. So 6 is there. Here you have to check. Is 4 less than or greater than 6? It is less than. Now you will go to the left subtree. Here 4 is found. Okay. So the advantage of this binary search tree is, if you want to search an element, since it is node based, you need not do unnecessary traversals. For suppose I want to search an element 1. So this is not, it's not there in the list. Suppose, for example, I want to search an element 7. First, what I'll do, I will check with the root node. In case if it is less than root node, I just have to traverse these 3 elements. Okay, I just have to traverse the 3 elements. In case, for suppose, it is like this. How many elements are there? 1, 2, 3, 4, 5, 6. Okay, if it is not like this, I want to search 7. Same 7. So if I want to search, I have to compare with the root node. Now I have searched with this. In case if I am not following this rule, I have to search in all these elements also, in case if there is no rule like this. Okay, so this is the advantage of binary search tree. Since it is node based, you can only traverse or search only up to an extent it is needed. You need not find unnecessary, make unnecessary traversal for visiting every node. Okay, for finding one node, you will have an appropriate, rule. You have to follow that and you have to find. Unnecessary traversals are not needed. Unnecessary memory wastage is also not needed. Right? So this is how you search elements. Right? Now we'll see the deletion. So in deletion, we have 3 types. 0 child deletion, 1 child deletion, 2 child deletion. Okay. So suppose, let's consider this tree. Let's make it easy. Suppose it is like this. Okay. Suppose my tree is like this. Suppose my tree is like this. Okay. So 70 has a node 80. Suppose This is my binary search tree and I wanted to delete, I want to perform zero chain deletion. Okay. So find out in this, what are the nodes to perform zero chain deletion? The nodes with no children. 4, 7, 21, 80. These are the nodes which does not have any children. Okay. In case if it is like this, you can directly delete this node. Okay. There are no other elements attached to it. Right. So you can directly delete it. Okay. So this is done. Now one child deletion. Okay. First, suppose you have an element like 15. Okay, you have inserted it. 15 is greater than 10. You have to go to the right subtree. 15 is less than 16. It went here, already occupied. So 21 is greater than, 15 is less than 21. So it went to the left subtree. Okay. Now I want to delete one child deletion. Perform one child deletion. What are the nodes which are generating single child? 16 is generating 2 children. 4 is generating 2 children. 21 is the only node which is generating one child. Okay. So now what you do is, this has to be deleted. 21. You want to delete 21. So if you delete 21 directly, this 15 is also there. So you will lose a node unnecessarily. So without losing that node, you have to make changes. Okay. Now consider the child node of that node to be deleted. Okay, this is the node to be deleted, and consider the child node and replace this place with its child node. Okay. Now it comes down. Okay, you have to make swapping. Okay. So this has become 15 and this has become 21. Now you can directly delete this. You did not lose this child right now. Okay. While you are performing the one child deletion, what you have done, it was 21 before. Okay. Now you have made this node as the leaf node. You have made this node as the child node of that, and you have interchanged the positions and you have deleted this node. So this node is not lost. Okay. This is how you perform one child deletion. Right? Now we'll see two child deletion. Two child deletion means the node which has two children. Okay. What are the nodes which has two children? Suppose 6. 6 is there. Okay. So what you do is, if you delete this node, you will lose these two nodes. But it should not happen like that. Okay. So now what I'll do? Now what I'll do is, I'll find the Inorder successor. What is the Inorder of this node? See, 6 is here. Successor means next. Inorder successor means the Inorder node which is coming after this particular node. Okay. Successor after, not previous one. This is my Inorder. After this, which Inorder is there? This Inorder is there. Okay. Now I have to replace the two child node. Okay. Two child node with Inorder successor. The next Inorder node which is coming next to that Inorder. Okay. The next one is 7. So you have to first replace it with this. Okay. Now it is 7 and this is 6. Now you want to delete 6, right? So delete it directly. Okay. So this is how you delete, or this is how you perform two child deletion operation in binary search. I will tell you one more example for two child deletion. Okay, this is my binary search tree. I want to perform two-child addition. So this is my two-child nodes. Okay, I want to delete this one, 32. I will see what is the in-order successor, what is the next in-order to this 32. So this is the previous in-order and this is the next in-order. After this, I am reaching this point. This is the pre-order. I won't consider that. This is the in-order. This is the in-order. Okay. Now I have to replace my node to be deleted with the in-order successor. This is the in-order successor. The next in-order to this node. Okay. Replace. After replacing, what has happened? 24, 26, and 74. Okay, this 74 has gone here and 32 is here. Okay, now you can directly delete this node. Two-child deletion is performed. Okay. So, when you want to delete elements for zero-child deletion, you can directly delete that element since there are no other elements connected to that. Okay, though there won't be any loss.